far in the second part of chapter 12 anyway, we've looked at combinations, binomial probability, and now we're going to look at another type of distribution called a normal distribution. And a normal distribution is a branch of statistical study that is probably the most common distribution to work with. It comes up in a lot of different venues, and if you take AP statistics, you will be using it tremendously in a wide variety of ways. So we'll start out, let's look at a picture of what the standard normal distribution looks like. The standard normal distribution is a bell-shaped curve. It's a bell-shaped curve that is centered at 0. It has a mean of 0, and it has a standard deviation of 1. So if we had a big bowl of marbles that each represented values on this distribution, if we pulled out all the marbles and found the mean, we would find that we have the mean of 0. Some of our scores are negative, some of them are positive. There are an equal number of positive, negative number values. You can see that I didn't show values beyond 3 and negative 3. However, there are numbers that occur off in the positive above 3 and below negative 3, but the frequency of those occurring becomes very, very small. So it's possible to have a number in the standard normal distribution that is a 3.2. It's just very unlikely for that to happen. It's much more likely to get a number that is between negative 1 and 1. In fact, 34% of the values in this distribution will be a value between negative 1 and 0. 34% of the values from this distribution will be between 0 and 1. So as I said before, the standard deviation of this distribution is 1. So if we did that calculation with a whole bunch of these values, we would get 1. And all of these values on the bottom are also called z-scores. So we're going back to what we studied at the very end of the first part of chapter 12, or that we already took a test over. So remember, a z-score was calculated by taking a score minus a mean divided by a standard deviation. That was our formula. Right now, we don't even have to do any type of a conversion. This is said to be a z-score of 0. This is a z-score of 1. Because the standard deviation is 1, a z-score of 1 will be 1 standard deviation higher than the mean. This is a z-score of 2, a z-score of 3, and etc. down this way. So in between these two values of negative 1 to 1, we have, again, 68% of our distribution is within 1 standard deviation of the mean. If we go out 2, you can't see it very well on this because it's in a shaded region, but this says 13.5% in here. It ends up within 2 standard deviations. So between a score of negative 2 to 2, 95% approximately of our values will be between negative 2 and 2. And if we go out to negative 3 to 3, about 99.7, get some lead here, 99.7% of our scores in a standard normal distribution will be between negative 3 and 3. So as I said before, it is possible to get a value that is lower than negative 3 or higher than 3. It's just very, very unlikely. Now, this curve has some other characteristics. The total area underneath the curve is 1. So if we found little squares and added up all of the area squares underneath this, it has an area of 1. There is a scale on this axis. There is actually an equation that involves an e power, the 2.718 number, raised to a kind of an odd exponent. But there is an actual equation that can be used to generate this equation that we're not going to go through. But what we do want to remember is that this graph does have the characteristic of being bell-shaped. That's what we typically call it. And it does have an area underneath it of 1. And that most numbers are within 3 standard deviations of the mean. And then there's something called the 68, 95, 99.7 rule that is kind of a nice rule of thumb to remember, because that does talk about within 1 standard deviation about 68%. Within 2 standard deviations, about 95%. And within 3 standard deviations, almost everything, 99.7% of our values will be in that range. Now, we have a table that we're going to use, and we have a lot of statistical notation that we need to go through. And to start with, let's look at this first question. I have find the probability that a random number chosen from the standard normal distribution from here is a number that is less than 0.96. So we know 0.96 would be about here on our chart. And I want to know if you had, like I said, a whole bunch of marbles that followed this distribution, put in a bag, and pulled out one of those values, what's the likelihood that that number would be less than 0.96? And we can see it's quite likely. We can see that 50% of the numbers are going to be below 0, so we're definitely going to be higher than 50%, and we need a way of figuring that out without using calculus, which is really one way we could do it. And I first of all like to draw pictures of what I'm finding. So I sketched a little normal distribution curve, centered it at 0, and I know one standard deviation. Oh, and let me go back up here a second. See how this graph has a characteristic that it's kind of bowling up, and then maybe about at this point it starts to bowl downward, kind of like a parabola going downward, and then it starts to bowl back up again here. This little point right here and right here, the graph is said to be concave down because it bowls down, and it's said to be concave up here because it kind of bowls up like a parabola that goes upward. Same thing here. These 2 points are called inflection points. And in calculus, we use that terminology at all. But for us, what we remember is if you can look at the normal distribution curve that you've drawn, the place where the concavity changes, where it goes from concave up to concave down, that is the mark that will be 1 standard deviation away from the mean. So when I graph this little bell-shaped curve here, again, I'm kind of eyeballing it, trying to make it symmetrical, but the graph is curving downward here, and then it starts to curve up. That's the mark where I would be 1 standard deviation away. All right, so I marked on here where 0.96 was, and I shaded to the left because I want values less than that, or the probability. I want the probability of getting a z-score from the standard normal distribution being less than or equal to 0.96. Now, we have a table that we're going to use for this because we can't eyeball this and just kind of guess. And like I said, unless we know calculus, we are going to have to use a table. And we need to turn to the side of this normal distribution table, and we need to find a z-score, and we can see that the z values are listed down here of 0.96. Well, when I go down, I only have the tenths place. When I go across the top, I see a 0.06. I need the intersection of this column and this row, and I go to 0.8315. And at 0.8315, that's actually the area to the left of a z-score of 0.96. So it's not only an area, it's a probability of this event happening. Oh, and by the way, I actually have here less than, strictly less than 0.96, so I don't have that little equality there. However, if I dot this line in and find the area to the left of it, as opposed to making it solid, it actually does not make any difference. The area that is strictly less than 0.96 in the standard normal curve will not be any more or less than if I, quote, include the line. Because including the line, this does not have any area. A line does not have 2 dimensions. It only has a length. Okay, so let's look at the second one. And you're going to see I'm going to be drawing pictures for all these. So I have on number 2, we're still using the standard normal distribution. Tomorrow we'll use many different distributions that are normal, but today we're just going to be working with the standard normal distribution. And I have find the probability that an observation from the standard normal distribution, which means I can sketch my curve right away. I know I'm going to have this bell-shaped curve centered at 0. Bowling down, maybe about there is where the inflection point takes place. So that's a standard deviation of 1 away. Trying to symmetrically go on the other side. And we want to find the probability that we randomly pick a number and that it is between 0 and 0.96. So we want just about that area. Now, we write that down in our notation. And now we have to have a strategy for utilizing our table. Well, we already know that the area from the previous question from 0.96 down is this 0.8315. But we also know that the area, half of the area is below 0. We could also take this table and go to 0 and see that the area below it is 0.5, but half the area is below. So if we take the difference between this number and this number, it will actually give us that shaded area between, and that's what I'm indicating here. Now likewise, I want to do the same thing on the next question. I want to find the likelihood that I have a value that is greater than negative 1.23. So I drew my little graph. You can see I estimated 1 standard deviation, 2 standard deviations away. I went to 1.23, estimated. I want greater than. Now I want to shade up above. I can see this answer isn't real big. So I write my notation down. What's the probability of choosing a z-value that is greater than 1.23? Again, if I had greater than or equal to, I truthfully would get the same answer. Now I have to look up this table. I still have a positive z-value, so I go to my table. I want to look for 1.23. Here's 1.2, and I have 0.3, and I have to find the intersection of these, and I find that that becomes 0.8907. But that's the area down here, 0.8907. I want the area above, and we know that the area underneath the whole curve is 1. So 1 minus 0.8907 will give me the area up above. So our table is always telling us the area to the left, and that's regardless of whether we have a positive z-value or we have a negative z-value. It's always telling you the area to the left of that value. Now, I want to find the probability that I choose a value from the standard normal distribution and it's less than negative 0.225. Again, I write my notation down. I draw my picture. And when I draw my picture, I know it is very unlikely for this to happen. It can happen, but it's not very likely because here's a negative 1z, a negative 2z, I'm negative 2.5. So I just have that little portion here. I would turn to the negative side of my chart, go to negative 2.5, and there was just 0, so there was no additional hundredths place, so it is 0.0062. And I have my answer directly. And the last one on this page, we want to find what's the probability you randomly pick a number, and it's between negative 1.5 and 2.25. I draw my picture. I know that's a large chance. So again, 0, 1, 2, positive 2.25 way up here, negative 1, negative 2 here, about negative 1.5, and I shade in between. I can see that the area has to be smaller than 1, but it's not far from 1. So I put my values down. To find the area between, you always look up the area underneath the larger z-value first. Find the area below the smaller z-value, and the difference between those will find the area between. So the area that is below this value is the 0.9878. If you look up 2.25 as a z-value and find the area to the left, and if I find the area to the left of negative 1.5, I get the 0.0668. And the large area minus the small area will give me the area between. A little bit more information we'll cover on this. And sometimes just the way the question is worded is the part that we have to look at and see how it relates to our thinking. So I have a set of data is normally distributed. What percent of the data is within 1.5 standard deviations of the mean? Within 1.5 standard deviations of the mean. This is what I want. This is my picture. And I calculated exactly the same way I did the other side. I find the area below 1.5, looking it up on my table, that gave me this. I find the area below negative 1.5, that gave me this, and the difference has the area between. Now, remember how I said the 68, 95, 99.7 rule? Here's our justification for that. Because if we're dealing with the standard normal distribution, or truthfully any distribution, but right now we're with the standard normal distribution, what percent of the numbers lie within one standard deviation of the mean? That is this question. And if I use the same technique that I used up above, I would be finding the area below 1, finding the area below negative 1, and taking that difference in the area. And notice how that's very close to 68%. I did the same thing for going out 2 standard deviations, very close to 95%. Did the same thing for 3 standard deviations, very close to 99.7%. So there's the 68, 95, 99.7 rule that we use in statistics to talk about being within 1, within 2, within 3 standard deviations of the mean. Now, sometimes our questions go a little bit backwards. In this case, I told you how many standard deviations away you were, and I wanted to find the area between those numbers. Now we're switching gears. I now want to figure out, if I know the area between two numbers, I want to know what the numbers are. So we want to find the symmetrical range about the mean. So the mean will be in the center of it, which includes 90% of the data. So this is really what we are looking at. We're trying to look at the distribution. We know if you go out 1 standard deviation, that's 68%. If you go out 2 standard deviations, you know that's 95%. So you know you're less than 2 standard deviations away. So we need to know what these z values are to tell how many standard deviations away we are. Now these are going to be opposite values. So our, and let me quick write up above here something. We're trying to find what z-scores, and again, these two numbers will be opposites, will have the area between them being 0.9. That's our question. These two numbers are opposites. So if we have the area underneath the whole curve is 1, and we want to have the area be 0.9 between these two, we're missing 0.1, 10%. That 10% divided by 2, I have 5% in each of what we call the tails. Now I'm going to go to this tail. I'm going to look up and find what z-score corresponds with an area of 0.05. Now, all of these numbers inside here are areas or probabilities. I have a value of 0.05 in here. And again, this is small. I'll zoom in here a little bit. And if I look for 0.05, I don't find 0.05. I find something very close. I find these two values. This one is tenths, hundredths, thousandths, 10,000ths. This is 10,000ths too big, 5 10,000ths too big. This one is 5 10,000ths too small. The z-value that corresponds with this value, if we look at the table, is negative 1.64. This value is negative 1.65. So, let me zoom out here a second. What we do is we actually split the difference on this one, because remember in our chart, if we had a 0.0505 and that corresponded with a z-value of negative 1.64, and we had a 0.0495 and that corresponded with a negative 1.65, that is split halfway between. We want the 0.05. So we go halfway between these two. And so these two z-scores are negative 1.645 to positive 1.645. So if we go out 1.645 standard deviations, that will include 90% of our data. Now, another type of way that I can give a question is to talk about a percentile ranking. And remember what it means to be a 75th percentile. 75th percentile, we're going to have, here's our normal distribution. And we know 50th percentile is at 0. We want to move this way. We want the area here to be 0.75. We want to know what number, oops, let me get that a z. what number has the area less than or equal to it being 0.75? So we would have to flip our page over, and we would have to look in the probability or the area part for 0.75 and find the number that's closest to it. And as I move along here, I have a 0.7486 and a 0.7517. This one is a tad bit closer. This is 14 10,000ths too small. This is 17 10,000ths too big. So closeness-wise, this one's a little bit closer, so we could use the 0.67. You could estimate and go about halfway in between because it is pretty close. And so it's between these two, really close, a little bit closer to this one. So if you're going to only use a two-place decimal, I would say 0.67. This is a little bit better estimate. You could even say 0.674, but we won't have to nitpick that much on it. All right. Okay, now you're ready to do some practice.